If you are working toward your Canadian certification in masonry, or you just have that burning curiosity about how buildings actually stay standing, this deep dive is for you. We are going right back to the absolute basics, looking at the unsung hero of every wall system, mortar.
And it's a huge topic. It's the material that provides the bond, the seal, the look, and yet, is so often dismissed as just mud or some kind of filler.
Right, just glue for bricks.
And that couldn't be a more dangerous misconception. Mortar is a highly engineered essential component. So today, we're cutting through all that guesswork and drilling right down into the technical specifics.
Okay, so let's unpack this. We're not just talking general ideas here. We're grounding this discussion in the reality of Canadian construction.
Yeah.
Where does that conversation even start?
It starts and it ends with the standard. For anyone in the trades here, this whole deep dive is rooted in the specs laid out in CSA A17914.
That's the mortar and grout for unit masonry standard?
That's the one. It's the absolute governing authority on how you bed, joint, and bond any unit masonry in this country. And the definition in there is the cornerstone of everything.
And what is that formal definition?
It's defined as a plastic or semi-plastic mixture of cementitious materials, aggregate, and water used for, specifically, bedding, jointing, and bonding units.
I noticed that wording immediately. Plastic or semi-plastic? That really points to the two different lives this material has, doesn't it?
It does. It has one job to do on the mortar board and a completely different critical job once it's in the wall. You have to master both states.
So these are the two critical states of mortar.
Absolutely. First, you have the plastic state. That's when the mortar is fresh, it's on your board, it's wet, workable, ready to spread. This is where the mason is in control.
You're adjusting the consistency.
You are. You might add water if the specs allow, or temper it. But here's the critical warning for any apprentice listening. You cannot judge the final quality of the mortar, its strength, its durability, while it's still in this plastic state.
So all the testing, the cylinder samples, that's all about the hardened state.
Precisely. Once that mortar cures or sets and it's in the wall, it transitions into the hardened state. And that's when it delivers its real purpose. The bonding strength, the compressive resistance, the weather sealing.
So when an engineer's spec sheet says, 1,800 PSI for Type S.
They are talking exclusively about its performance in the hardened state. And I should also note that CSA A17914 standard also covers grout.
Which is different.
Very different. Grout is thinner, more flowable, and it's designed only for filling cores or cavities, not for bedding the units.
Okay, that sets the baseline perfectly. So our mission today is a full immersion. We need to break down the components, detail the 4 non-negotiable functions of mortar, and then really master that classification system MSNOK and understand why you choose one over the other.
A perfect roadmap. But before we get to the functions, let's just acknowledge that mortar's main job is, well, it's to attach two things together.
And sometimes attachment can be a complicated business, which reminds me, why did the mortar go to therapy?
Oh, I think I know this one.
Because it had attachment issues and felt like it was always being stepped on.
That is a fitting, if maybe a little too literal, description of its role.
Let's get serious about that job description now. You say mortar does 4 things, 4 distinct, equally vital things. What are they?
We define them as bonding, weather resistance, unit size compensation, and finally, appearance or aesthetics. And if you fail on any one of these, the entire wall system is compromised.
Even if the strength is there.
Even if the compressive strength is technically fine, the system fails.
Okay, let's start with function number 1, bonding. This is the one everyone thinks they understand, but what does good bonding really do for the structure?
It's the primary role, yes. But it goes beyond just sticking things together. It's about binding all those individual units, brick, block, whatever they are, into one single monolithic system.
So it's about stress resistance.
It is critically about stress resistance. When you're designing a wall, you're not just worried about gravity. You're constantly worried about lateral forces.
Like wind loads on a tall building, seismic activity, or even just soil pressure on a basement wall.
Exactly. The mortar has to develop enough tensile and shear strength to resist forces that are trying to pull the wall apart or slide courses past each other. If that bond is weak, the wall will fail right at the mortar joint.
Okay, function number 2 is maybe the most critical for just surviving in the Canadian environment. Weather resistance.
This one is completely non-negotiable. The mortar is the weather seal for every joint, preventing moisture from getting into the wall assembly. But here's the key for an apprentice. Getting good weather resistance is only partly about the mix.
What's the other part?
It's overwhelmingly about execution and timing.
You mean tooling the joint?
Precisely. The finish you put on that joint is what sheds the water. A good concave or V-joint directs water away. But the timing of that tooling is everything. You have to do it at the right moment, which we call thumbprint hardness on the job site.
Describe that for someone who hasn't felt it. What is thumbprint hardness?
It's that sweet spot. It's the moment when the joint has stiffened up just enough so that when you press your thumb into it, it only leaves a faint, subtle trace, not a deep dent.
And if you tool it too early, when it's still wet,
You'll just smear the surface.
Yeah.
You end up dragging excess water to the face of the joint, which weakens that crucial boundary between the mortar and the unit. You get a poor, low-density, brittle surface that will let water in.
and if you wait too long.
Tooling too late is just as bad. The mortar has already started its final set. You risk disturbing the bonds that have already formed, creating micro cracks, and the joint surface just gets crumbly, and you can't compact it properly.
And in our climate, with freeze-thaw cycles.
A poor weather seal is a death sentence for a wall. Water gets in, it freezes, it expands, and it just destroys the mortar and eventually the units from the inside out. The standard demands integrity, and integrity demands perfect timing.
That makes the workability of the mortar so important, which leads us perfectly into function 3, which is pure practical reality, unit size compensation.
It's the ultimate utility function of mortar. I mean, despite all our modern manufacturing, masonry units are never perfectly identical. Clay units shrink a bit in the kiln. Concrete units have slight variations.
So you might have a few millimeters of difference here and there.
Exactly. And if you tried to just stack those units dry, those tiny imperfections would add up fast. Your wall would lean, it would twist, it would look awful.
So mortar is basically the great equalizer.
It is. It's the plastic layer that absorbs those imperfections. A skilled mason uses the mortar bed to make tiny adjustments, keeping every single course straight, level, and plumb. Without that plasticity, it would be an impossible job.
And that plasticity comes from.
It comes from a good mix, usually with the right amount of lime, which we'll get to.
Okay. And finally, function number 4, appearance, aesthetics. This is where the architect's vision meets the mason's hand.
Absolutely. The mortar joint is the visual framework. It defines the pattern, the texture, the whole look of the finished wall, the color of the mortar, the texture of the sand, the type of joint. It's all part of the design.
So what about colored mortar? How is that achieved and controlled?
Usually it's done with highly stable metallic oxide pigments or sometimes ground-colored aggregates.
And there are limits on how much you can add.
Yes, the CSA standard is very clear. The coloring admixture shouldn't exceed 10% of the cement content by mass.
Yeah.
Any more than that, and you risk interfering with the chemical reaction of hydration, which can weaken the mortar.
But the biggest challenge, I imagine, is keeping that color consistent across a huge wall.
That's the real trick. And it's why pre-blended, factory-mixed mortar is so often specified.
Why is that so vital?
Because there are so many things that can change the color on site, even with the same pigment. The pigment-to-cement ratio might vary slightly if you're mixing by hand. The water-cement ratio is huge. More water means a darker mortar.
I didn't realize that.
Oh, yes. And the most overlooked factor is tooling time. If you tool the mortar when it's wetter, it will be darker than if you wait until it's drier. So to get that seamless, uniform look, everything has to be identical.
The materials, the water, the mixing, the timing.
All of it. And that level of control is just much, much easier to achieve with a factory blend.
Okay, we've established what mortar has to do. Now let's break down the chemistry, the secret sauce. We're talking Portland cement, hydrated lime, aggregate or sand, and water. Let's start with the one that provides the raw power, Portland cement.
Portland cement is the strength agent, period. It's what turns that plastic mix into a hard, durable solid. It's a hydraulic cement, which means it needs water to set and harden. Its main job is to drive the bond strength, the durability, and especially the compressive strength in that final hardened state.
And that setting process is called hydration.
Correct. Hydration is the chemical reaction between the cement and water. It forms a gel, calcium silicate hydrate, and that's the glue that binds everything together. For new construction, we're typically using Type 10 Portland cement, which is now known as GU, or general use.
So here's the big question for an apprentice. If cement provides the strength, why don't we just load up every mix with as much cement as possible?
That is the most important question.
Yeah.
Because it defines the fundamental trade-off in all of masonry. More cement does equal more compressive strength, yes, but it also means poorer workability when it's plastic.
And in the hardened state.
More critically, when it hardens, the mortar becomes incredibly rigid and brittle. It has no flexibility. It can't handle the tiny movements that every building goes through: thermal expansion, wind deflection. A high cement, brittle mortar will just develop microcracks.
Which compromises the weather seal we just talked about.
Exactly. It lets
Yeah.
water in. So cement is the brute force. But you need a countermeasure.
Something that provides finesse, elasticity. And that brings us to hydrated lime. What is its main job?
Lime is the workability and healing agent. In the plastic state, it's a mason's best friend. It dramatically increases water retentivity.
So it helps the mortar hold on to its water.
Yes, which keeps the mix plastic, buttery, and easy to spread for a lot longer. This is especially important when you're laying absorbent bricks that try to suck the water out of the mortar too quickly. We generally use a Type S hydrated lime.
And we need to be very clear here. Type S hydrated lime is a component. It is completely different from Type S mortar, which is a final mix designation.
A critical distinction, absolutely. Type S lime is just a specific high-quality grade of hydrated lime that's ideal for use in masonry.
Okay, so that's its role in the plastic state. What about its role in the hardened state? You called it the healing agent.
Yes, this is the magic of lime, autogenous healing. In the hardened state, the lime, which is calcium hydroxide, provides bonding and, crucially, elasticity. It allows the joint to flex slightly under stress instead of just cracking.
And the healing part.
The healing comes from carbonation. If a tiny hairline crack develops from, say, thermal movement, the calcium hydroxide in the lime reacts with carbon dioxide from the air and any moisture present.
And it recrystallizes.
Exactly. It forms calcium carbonate, which is essentially limestone, and it seals that crack. It's an incredible, natural, self-healing mechanism that a pure Portland cement mix just doesn't have.
No, it's a trade-off. You increase the lime, you decrease the compressive strength, but you gain this incredible durability and flexibility.
That's the balance. A wall needs to be able to move a little. An old-timer on a job site once told me something I never forgot.
What's that?
I asked him why he adds so much lime to his mix. He said, "Son, if I wanted to build something that never moved, I'd be a statue. I want this wall to breathe, not have a midlife crisis."
That's a great way to put it. That breathing room is the lime.
It is. Now, before we move on, we should just quickly touch on the different types of lime. We've mentioned hydrated lime, but there's also quicklime. Quicklime is caustic and has to be slaked with water to make lime putty. And the standard says that putty made from quicklime has to age for at least 24 hours. If you make it from the safer hydrated lime powder, it still needs to age for at least 12 hours to improve its workability.
Good to know. Okay, moving on to the biggest component by volume, the aggregate. Sand. It's more than just a filler, isn't it?
Oh, sand is crucial. It adds strength, volume, and helps with workability. But its most critical job is reducing shrinkage. A pure cement lime paste would shrink and crack as it dried. Sand provides the stable skeleton.
And the quality control here is all about gradation, the size of the sand particles.
Correct. You need a well-graded sand with a good mix of particle sizes. The smaller grains fill the voids between the larger ones. This gives you a dense, strong mix.
What happens if the sand is poorly graded? Say it's too coarse.
If the sand grains are too large, the mortar feels harsh and gritty. It's almost impossible to spread smoothly. If the grains are too fine, the mix is weak, it needs too much water, and it's prone to shrinkage, and it has to be clean.
No dirt, no organic matter.
Absolutely nothing. No oils, no salts, no ice. Organic matter is especially bad because it can completely mess with the hydration process and stop the mortar from setting properly.
And finally, the simplest ingredient, water. It has to be clean, but what else?
It has to be potable, drinkable, free from acids, alkalis, oils, anything that could interfere with the chemistry. If your water source has salts in it, those salts can later leach out and cause that ugly white staining on the wall we call efflorescence.
We talked about consistency for color. That means using the same water source for the whole job.
You have to. And you have to be careful about tempering or adding water on site to an older batch of mortar.
Right, because it changes the color.
It changes the color, yes, but it also increases the water to cement ratio, which reduces the final strength and durability of that batch. Best practice is to use your mortar within about 2 to 2.5 hours of mixing, and avoid tempering if at all possible, especially if color is critical.
Okay, we've got the components, and we understand the big trade-off. Strength from cement versus flexibility from lime. And that balance is what's codified in the classification system. For anyone studying, there's a mnemonic to remember the 5 types. Mason work, MSNOK.
That mnemonic is your best friend, but understanding the philosophy behind it is what makes you a good mason. The fundamental rule is this: As you go down that list from M to K, you are systematically lowering the cement content and usually increasing the lime content.
Which means?
It means compressive strength goes down, sometimes by a lot, but flexibility, elasticity, stickiness, and that self-healing ability, they all go up. You're swapping raw strength for the ability to handle movement.
Let's start at the top of the strength scale then. Type M mortar.
M for max strength. This stuff is almost pure cement. A typical mix is 1 part Portland cement, only 1/4 part lime, and about 3.5 parts sand.
So with that little lime, what are its properties?
It's extremely rigid, very, very brittle. It has the highest compressive strength, but minimal elasticity. It's really only used for things that need maximum load-bearing capacity, like below-grade foundations or work with hard stone like granite.
So you wouldn't use it on a regular brick wall?
You should not, especially not with softer units like concrete brick. The mortar would be stronger than the brick itself, and any movement would actually crack the brick, not the joint.
Okay, next up is the real structural workhorse, Type S mortar.
Right. S is for structural strength. It's in that medium-high strength category. It has excellent durability and strength, but its real claim to fame is its maximum bond strength and fantastic resistance to lateral forces.
So wind, soil pressure.
Exactly. This is what you use for retaining walls, reinforced masonry, structural cores, anything that needs to resist being pushed sideways. A typical mix has a bit more lime, maybe 1 part cement, 1/2 part lime, and 4 to 4.5 parts sand. The strength is usually around 1800 psi.
So if Type S is so strong, why don't we just use it everywhere above grade? Why bother with Type N?
That's a great question. And it comes back to that trade-off. Type S has more cement, so it costs more. But more importantly, a mortar that's too strong for the job can be a bad thing. For a typical brick veneer, Type S is overkill, and it's still pretty brittle compared to Type N.
So let's talk about the champion of general use, Type N mortar.
Type N is the normal or general use mortar. It's the most common type you'll see specified in Canada. It has a good medium compressive strength, but its real benefit is high elasticity and that great self-healing ability from the lime.
What's a typical mix for N?
A very common one for exterior veneer is 1 part Portland cement, 1 part lime to 6 parts sand, a 1-1-6 mix.
And its uses are, well, general.
It's everywhere. Exposed masonry above grade, brick and stone veneers, chimneys, non-load-bearing walls. When you don't need massive compressive strength, Type N's flexibility gives you the best long-term performance against thermal expansion and contraction.
Okay, now we're moving into the specialty mortars. Lower strength, higher flexibility, starting with Type O.
Type O is for old or restoration work. It's a medium-low strength mortar, very soft, very flexible, very high in lime. A mix might be 1 part cement, 2 parts lime to 9 parts sand. The strength drops way down to around 350 psi.
So why on earth would you ever want a mortar that weak?
This is a really profound conservation principle. We call it the sacrificial material concept.
Sacrificial?
Yes. You use Type O for repointing old historic buildings, where the original bricks are often softer and more porous than modern ones.
Okay.
If you repoint that old soft brick with a hard modern Type N or S mortar, any movement or stress will be transferred to the weaker material, which in this case is the historic brick. The brick face will spall and break, but the new mortar will be fine.
So you're intentionally designing the mortar to fail first to protect the original unit.
Exactly. The mortar sacrifices itself. Its softness and flexibility mean it absorbs the stress and the weathering.
Right.
When it wears out, you just replace the mortar, not the priceless, irreplaceable historic brick.
That's fascinating. And at the very bottom of the scale, we have Type K.
Type K is for classic. Very low strength. This is basically what was used before Portland cement was common. It's almost all lime. A mix might be 1 part cement, 3 parts lime, and 12 parts sand.
And the use case for that today?
Almost none, really. Interior, non-load-bearing partitions, some very specific historic restoration. Mostly it's used in training programs to teach students about workability and plasticity.
So we've run through the whole alphabet, MSNOK. But for a Canadian apprentice working on modern jobs, the field is actually much narrower, isn't it?
It is. This is a critical regulatory note.
Right.
While it's important to know all 5, the CSA A179 standard only specifies detailed requirements for 2 types for modern engineered masonry, Type N and Type S.
So M, O, and K are really for specialty situations.
Exactly. They're addressed in annexes for things like repair and restoration, but for new structural design, it's all about N and S, for general use, where flexibility is key. S for when you need that structural punch and lateral resistance.
I think we've covered the whole alphabet. I did hear about an apprentice on a site who asked the foreman why there wasn't a Type P mortar.
Oh, That old one. What did he say?
He told him, because after you spend all day mixing M, S, N, and O, you're too tired to pee anyway.
That's an old one, but it's a good one.
Okay, that brings us to the practical side of things, the real-world application on a Canadian job site in our climate. You mentioned that specs are written as either proportion or property specs.
Right, and it's a crucial difference. A proportion spec is the recipe. The engineer says use a 1:1:6 mix for type N, and as long as you follow that recipe, you're compliant.
And a property spec.
A property spec is about performance. The engineer says your mortar must achieve a minimum compressive strength of 1,800 psi. They don't care as much about the recipe as long as the final product, proven through lab testing, meets that structural demand.
And that's more common for highly engineered structures.
Yes, especially reinforced masonry. But regardless of the spec type, consistency is everything. You cannot overstate this.
Using the same brands, same sources.
Same brand of cement, same source of sand, same source of water for the entire project. If you switch halfway through, you are asking for problems with strength, setting time, and almost certainly color.
Which is where ready-mix mortar comes in.
It's a huge advantage for quality control. It comes pre-blended from a factory, sometimes even pre-mixed with water and special admixtures that can keep it workable for up to 36 hours.
36 hours? That's incredible compared to the 2-hour window for site mixed mortar.
It's a game changer, and it guarantees that every single batch meets the exact same proportions. It takes human error out of the mixing process on site.
Let's shift now to the biggest challenge, our climate. Durability against frost, against freeze-thaw cycles. How do we design mortar to survive that?
The key concept here is air entrainment. Water expands by about 9% when it freezes. If that happens inside the mortar, that expansion creates immense pressure and just blows the mortar apart from the inside.
So we intentionally add tiny air bubbles.
We create millions of microscopic pressure relief valves. The CSA recommends that for our climate, mortar should have about 8 to 15% intentionally entrained air. When moisture freezes and expands, the pressure pushes into these tiny empty voids instead of cracking the mortar matrix.
And how do you get that air in there?
You either use a type SA lime, the A is for air entraining, which has an additive in it, or you use a standard type S lime and add a specific air entraining agent during mixing.
Now for the ultimate challenge, cold weather construction. The standard gets very strict when the temperature drops below 5 degrees Celsius.
Yes, because the freeze risk becomes critical. If fresh mortar or grout freezes before it gains enough strength, say 500 psi, the hydration process just stops dead.
It pauses until it thaws.
It does, but worse than that, the expansion of the water as it freezes can physically break the bonds that have already formed, causing permanent structural damage.
What does that damage look like?
A classic example is pouring grout in a bond beam on a cold day without protection. If it freezes, the expanding ice will literally push the blocks apart, causing a horizontal crack right along that course. It's often irreparable.
So contractors have to heat the materials. Water's easy, sand is not.
Water is the easiest, for sure. Sand is tough. It's labor-intensive and expensive to heat a giant pile of sand. A common method is to run perforated pipes or culverts under the pile and circulate steam or hot air through them.
But you have to be careful not to overdo it. The danger of scorching the sand.
This is a crucial caution for every apprentice. Sand has to be heated slowly. If you scorch it, it gets a reddish, burnt tint, and it's chemically altered. It can accelerate the set time of the mortar, making it stiffen up way too fast.
So scorched sand is unusable.
It has to be thrown out.
Yeah.
And beyond heating the materials, you have to protect the wall after it's built.
Tarps, enclosures, heaters.
All of it. The CSA requires you to keep the temperature of the masonry above a certain minimum for typically 72 hours until the mortar is strong enough to resist freezing on its own.
Which brings us to the final and often most contentious point. Who is responsible for all of this?
This causes so many arguments on job sites. Who pays for the heaters? Who builds the enclosure? Who monitors the temperature? It's absolutely imperative that all of the heating and protection responsibilities are clearly defined in writing between the masonry contractor and the general contractor before the job starts.
Clarity avoids conflict and, more importantly, avoids failure.
Exactly.
We have had an incredibly comprehensive deep dive. To try and synthesize this for the learner, mortar is not simple. It's an engineered material defined by 4 functions: bond, weather seal, size compensation, and appearance.
And that classification system, MSNOK, is a sliding scale. More cement means more strength, but also more brittleness, More lime means more flexibility and that amazing self-healing ability, which is key to long-term durability.
And for modern Canadian construction, the choice really boils down to type S for structural needs versus type N for general use.
And success on the job site comes down to absolute quality control. Consistent materials, perfect tooling time at thumbprint hardness, and in our climate, rigorous air entrainment and cold weather protection.
To leave our listeners with a final thought, what would that be?
I'd go back to that idea of typo mortar being a sacrificial material. I'd prompt you to think about why it's better to have a weaker, more flexible mortar when dealing with historic buildings. Think about how the relative absorption rate of the mortar actually protects the historic brick or stone by wicking moisture out of the unit itself. It's a choice driven by preservation, not just by raw strength.
An excellent thought to consider, especially for the heritage side of our trade. Thank you for this essential technical deep dive.
My pleasure. Keep your courses straight and your consistency consistent.
Next time, we're diving into the tools and processes, mortar mixers, quality control testing, and detailed considerations for both hot and cold weather construction.